Good afternoon, everyone. Thank you for joining us. This is our Radio Shop chat for today. And I'll take a few moments to summarize this series. My name is Nick Lanneman. I'm a professor of electrical engineering at the University of Notre Dame, and I'm serving as center director for Spectrum X. And if you hit the next slide, Julie, this seminar series is part of our initiative, which is the NSF Spectrum Innovation Center. This is kind of the layout, a map of our center as it stands today with 27 member institutions and just over 150 researchers taking a broad set of expertise in addressing spectrum issues and trying to move how we use spectrum and make efficient use of it forward in this country. If you go to the next slide, Julie. The tagline for Spectrum X that we're trying to create an academic hub in this big, glorious, complicated radio spectrum ecosystem to make it easier for academics to engage across the ecosystem and contribute to regulatory and policy proceedings here in the US and even at the international level. So the next slide, Julie. The one way we engage is we host these radio shop chats. So this is a series of seminars. It's not just for our center, but it's for the entire radio spectrum community. Everyone on the mailing list is invited to these events. During the session, we are, it's essentially a presentation and some Q&A. We do work with the speakers to get their permission to publish the slides and publish a recording of the video. But while we're waiting for those approvals, everything you learn here today, we operate under kind of a modified Chatham House rule. So you're free to use the information, but you can't quote anyone or attribute anything to an individual without their permission. But again, over time, more often than not, the speakers allow us to publish their slides and publish the video recording of the session itself. We're already at our normal set, roughly average set of participants in terms of numbers, but hopefully we've got some newcomers and we welcome you. If you go to the next slide, Julie, if you're interested in getting more involved or finding out more about Spectrum X, here are some quick links. We've got an opportunity for you to track us both through the web and LinkedIn. And if you want to share your contact information, we are happy to add you to the mailing list as well. Okay, with that, let me introduce today's speaker. I'm really excited to have Andy Molisch join us. He's been sort of on my wish list as a Radio Shop chat speaker for some time now. Many of you know that Andy is very accomplished. He's been both in industry at AT&T, Bell Labs, and at Mitsubishi Electronic Research Labs, which is where I got to learn of Andy and get to know him. Published a number of papers, several books, including the third edition of his wireless book that I have on my shelf here behind me. But he's really well known for experimental work, propagation measurements, and in innovating in the context of wireless standards. And I know he's been up to some interesting things for several years now, and we haven't had an update in the context of Spectrum X and spectrum management. And so we're really excited that Andy's agreed to join us and give us that update here today. Andy, I'll hand it off to you.
Yeah, thank you very much, Nick, for the kind introduction. So it's a great pleasure to be here. So thank you for inviting me here. Thanks everybody who's attending. And I'll try to make it worth your time to listen to this talk. So I want to talk a little bit about different measurements and modeling aspects that we've been exploring in the past couple of years and that are mainly concentrating on urban environments. Now, just before I go into this, let me give you a one-slide introduction of my research group at USC. So we are basically focusing on one hand on propagation channels and on the other hand on wireless system design, and in particular then the interaction between the two. So the fact that we are also very interested in system designs will shine through in some of the discussions today, because the measurements that we're doing are really motivated by the fact that, well, they are needed for certain particular system aspects and implications, and I will refer to them from time to time, which of course then also has the strong connection to the actual spectrum assignment, because the question of how the spectrum world depends on the propagation conditions ultimately also relates to the fact of how will that impact the overall system design. Now, in terms of the propagation research itself, our main emphasis is on saying that we want to have a holistic view of the whole propagation, which means that we are building our own channel sounders, create algorithms for the evaluation of measurement campaigns. From there, go to modeling aspects, and if necessary, introduce new models, and bring this overall then into standardization as far as possible. Little side note here, and want to make a little bit of advertisement, that there is a new IEEE group, P1944, that is developing 6G standard channel models. And if you're interested in, I'd be more than happy to introduce you there. I'm heavily involved in this.
Hey, Andy,
So,
I'm
yeah.
really sorry to interrupt you, but I'm not seeing your slides. Are others seeing your slides?
No.
Oh, that is funny.
I apologize. I think there
No,
might have been a
I
transition.
apologize. That's rather important that we have the slides visible.
Aha, I see
Can
slides now. So how many
do you see
slides?
it?
You're on slide 3, it appears.
Right. Do you see full screen slides, or do you see the presenter preview?
Now they're full screen.
Full screen. Okay, great. Yeah, sorry, we tested before, but for some reason it didn't work now. Okay, so anyway, I think not much harm done. So the first slide that I was presenting here was really just talking a little bit more about the group at USC and the sort of type of work that we are doing here. So I think jumping now into a little bit more on the motivation of the propagation channels, I think in a group like this, I don't really have to spend a lot of time motivating why we are investigating 6G and why we are looking at propagation channels. But let me just stress again that what I like to call the first axiom of system design, right? In order to design a good wireless system, we have to take the channel into account. And the question of why do we need new channel models, I think that's maybe a little bit more, it deserves a little bit more argument, because one thing I hear even from experienced researchers from time to time is, well, we've got the 3GPP models, so why do we still need to do new measurements, create new models? And the answer to that is twofold. Firstly, these the 3GPP models, or more generally, the existing models, are typically designed for systems that have certain deployment scenarios and certain frequency bands in mind. So as we are now going, for example, to distributed massive MIMO systems, as we're going to new frequency ranges, we can't just say, oh, we're using the channel models that were based on measurements done at the traditional cellular frequencies with the traditional structure. And that is not going to work at all. And the second reason is that the 3GPP models and a lot of similar types of models are aimed to compare systems, but not to provide absolute performance. And so if we have a common offset by 20 dB in our receive power, to pick just one particular example, right, then that doesn't influence of whether system A or system proposal B is better, and 3GPP can easily make a decision based on it. But if we're trying to make a decision about spectrum allocation and how much interference we're going to see and so on, then if we're 20 dB off, then that is pretty catastrophic. So we've got to be careful about which models can be used in what context. And so as we are going now to more location-specific considerations in terms of spectrum planning, as we are going to new deployment methods and new frequency bands, we do need more measurements. Now, some of the challenges that we're experiencing for 6G is that, first of all, the measurements need to be directional, right? We have smart antennas, probably massive MIMO now pretty much everywhere. So we need to actually know the directional characteristics. The combination of needing directional characteristics, potentially distributed systems, new frequency bands, and so on, is resulting in an enormous increase in expense and time of measurement campaigns. And I think, again, in this forum here, a lot of us know the problem that maybe 30, 40 years ago, you needed a narrowband transmitter and a spectrum analyzer, and you could do a measurement campaign. And nowadays, it's hundreds of thousands of dollars of equipment to measure anything that's interesting. In terms of modeling, also, we are encountering new challenges and things that are emerging as important that maybe were not so much under consideration previously. For example, diffuse multipath, the question of whether we can just use an isotropic path loss model in urban environments, whether we are still in the far field. And these are all things that are becoming challenges in 6G. So before I'm going to go into the separate items, I want to start out with the main takeaways. So I'll be talking about 4 different topics. Distributed massive MIMO systems, where we're going to see that, well, first of all, to measure them, we are going to need new approaches. Then secondly, and very importantly, our Euclidean distance path loss law models break down completely when we're in an urban environment. So just saying path loss is proportional to d to the power of minus n is not going to work anymore. Shadowing is also becoming non-stationary, and rather we have to do a sort of street-by-street path loss modeling. The next aspect I'm going to discuss is channel modeling in the upper midband. And so the work in that area has started. We see this upper midband really as the transition between the traditional cellular and the millimeter wave band. And one of the things there is vegetation is really becoming quite critical, but also in order to allow a good characterization and planning for the future, well, the upper midband is fairly wide, relatively speaking. We're thinking 6 to 24 gigahertz. So just doing point-wise measurements at 7 gigahertz only is not really going to tell us enough. So we need to explore more. For sub-terahertz, we've done a lot of measurements, and one of the key insights is that it is much richer multipath than the theory predicts. We see a lot of theory that says, well, maybe we've got 5 or 8 strong paths, and that's it. And we've seen hundreds, if not thousands, of paths. And so this has, again, big impact on on transceiver structures, equalizers, possibility of interference suppression, and so on. And diffuse multipath actually plays an important role, especially at sub-terahertz, but also at other bands. And last but not least, when we're talking about line of sight probability, it's also interesting that the models that we have, for example, from 3GPP, are based actually on a couple of European cities, but what's actually happening in the US has never been really explored. And so we did some recent work there and showed that, yeah, if we're looking at the real world deployment scenarios in the US, things are quite a bit different from what the existing models are. So this was sort of the outline of the highlights. Now I'm going to go through the different topics one by one, and I'll be happy to stop after each of those subtopics, and we have questions there. And yeah, let me start out by looking at distributed massive MIMO systems. So there we basically say we want to have a lot of different access points that can have a connection. Oops, sorry, my slides are jumping by themselves. we have a lot of access points distributed throughout an urban environment, and we are now looking at the possibility of combining the signals from the access points, which means that we need to have a joint characteristic of the path loss as the very first item to the different access points. And if we were now just dealing with this Euclidean path loss law, then, well, things would be very easy, and that's actually what a lot of the theory is doing. But unfortunately, it is not corresponding to the reality. So I'm showing here at the bottom a little bit the measured, or I think in this case it was ray traced path loss as a function of the Euclidean distance, and the fitted model that we are getting with the traditional linear least square fitting is the yellow line here. And the red points would be what we're getting when we simulate with the appropriate sigma standard deviation around it with log normal shadowing. And the blue points is what we're actually getting from ray tracing. And you see here that we can be completely off, that our path loss could be 20, 30 dB lower or 50, 60 dB higher than what this linear least square fit gives us. And the reason for that is that, well, if we are in such a waveguiding environment like here, then obviously we do not have a Euclidean law that is corresponding. So I've given here a little bit of a literature survey of what has previously existed in terms of measurements and models for this distributed massive MIMO. Apologies, I'm not going to go through the list in detail, but you'll have it in the slides. But we said that, well, ray tracing is nice and good, but let's actually try and measure the whole thing. And one of the problems with measurements is that if you even set up 3 or 5 access points, and then typically you need access or permission to put them somewhere up there. You need to fiber connect them to your receiver so that they are synchronized and so on. And so even a very small number of access points becomes a problem. We wanted to have a much denser grid of potential access points. And we came up with the thought that, well, let's just make the access points a virtual array. And it's fairly common for people to measure different UE locations by means of a virtual array, meaning we just have a single UE and we move that mechanically. But we said that, no, we actually want to do that with the access points. And we did this in 2 different measurement campaigns in 2 different ways. One was to take a drone and basically fly that a little bit or close to rooftop height around, and every location that the drone passes basically now becomes a potential access point. And then we did something very similar with a cherry picker based system, which has the advantage that we can have a heavier and more precise transmitter on the system. We have slower movement, and we overall have a better control over the system. But what it means ultimately is that we got somewhere around 10,000 different access point locations. We combined that with a number of UEs that were connected to a channel sounder in a switched way. And so, long story short, very detailed picture of what happens in distributed massive MIMO systems. Now, what you see here is just a sample measurement where we basically moved our virtual AP along all these locations here in an urban environment. This is actually on our campus. And here you see plotted the impulse response as a function of time, or rather, I should say, location of that virtual AP. And so this is actually a measurement campaign in which we resolve the individual echoes. We're still it's working on the modeling of the PDPs, and we've verified where all these different echoes are coming from. But what we did based on the first drone measurement campaign is to establish a new path loss model. that's maybe for today the more important aspect, because it's very general. It says that, well, mainly the path loss is determined by the order of the street that I'm in. And by order, I mean, well, if I'm the UE here, then I can see an access point with line of sight. That would be a 0th order street. Or I require one bending around the corner. That is a 1st order street. Or I might require 2 bendings around the corner. This is a 2nd order street. And for each of those streets, we are getting separate path loss laws. And essentially, you can say that, well, I have some path loss up to here. Then I have a loss to get around the corner. And then I have another path loss coefficient and another path loss for that stretch of the street here. And so obviously now any access points that are all in this street here show a very strong correlation of their path loss. Access points that are in this street here, and they are correlated amongst themselves, but they are pretty decorrelated from the ones in this street down here, because, well, I have a different propagation up to the corner. I have a different bending loss, and then I have a different path loss coefficient. Maybe the street is wider or the building structure is different when I'm going here. And so this is, as I said, a very different approach from looking at the Euclidean path laws, but it results in a stochastic model that's obviously quite a bit more complicated with more parameters than what we would normally have. You see here the list of the different parameter values and statistics. But to make life easier for everybody, we actually created a MATLAB program and made it publicly available that you can just download, and you can put in parameters that are characteristic for your environment, like the street width and the size of the blocks in the urban environment. And it now generates correlated path loss and shadowing values for you for the simulation of such distributed massive MIMO systems. And we validated it with some ray tracing, and that was done in Manhattan. You see here, well, if we're in a line of sight street, then the difference between between this CUNEC model, as we call it, and the standard model is not that big. And because it's dominated by line of sight. Physics is physics. There's nothing to change it. But once we're going to non-line of sight, you see that the standard alpha beta model would basically give us an almost constant path loss as a UE is moving along a side street, because the Euclidean distance doesn't change very much in this example here. But as we are going deeper and deeper into the street canyon, away from the corner where the bending had happened, the actual measured path loss, which we see here, is, of course, changing a lot, right? By 30 dB or something like that. And you see here that qualitatively, the CUNEC model properly follows what the ray tracing is doing. Because one is statistic, the other one is for one particular ray trace trajectory. Of course, we are not getting 100% agreement, but the fundamental behavior, the physical correctness is there. So that's maybe a good point to stop and see whether we have any questions concerning this.
Could I ask a question?
Mm-hmm. Go ahead, please.
Thank you. Why did you say that this model is not valid for cell-free massive MIMO? I thought I saw a note in your slides.
No, I was saying that the standard Euclidean distance model is not valid for cell-free massive MIMO in an urban environment. So the CUNEC model is actually specifically designed for cell-free massive MIMO.
Okay, I misunderstood. Thank you so much.
I think I see another raised hand. Richard Reza.
Yes, sir, Fraser. I'm curious, is there any application to like AI in terms of helping you with navigate all this math, or is that would that even come into play? Because there's a lot of uncertainty, I think, in some of your math in terms of because you're basing on sort of a static, fixed thing that makes assumptions. But is there some way that AI could be? It's just been a lot of talk about AI-enabled channel modeling at NIST and other places. So what's your view of that?
Yeah, I mean, I'm not sure how to relate this directly now to the distributed massive MIMO and these particular measurements here. Generally speaking, I think we are ourselves working on applying AI in some of the channel modelings, but there are significant obstacles, I think, for a number of applications. So a lot of the work is done with generative adversarial networks. We've actually looked at transformer-based foundational models as well. One of the key difficulties, or I see two difficulties here. The first one is the question of hallucinations and how you prevent the models from going completely off the rails. And I think that is an issue very generally in AI, but it might be even more significant here for the channel systems. The second challenge is the availability of good data for training of the AI and the verification. And that is actually one thing where there is a lot of activity going on, where we have actually also some joint work recently with NYU, in which we were looking into that question of, well, how can we at least formulate the results of measurement campaigns in such a way that AI would be able to take not only, let's say, our data and NYU's data, but pretty much data from everybody and get a broader overview of what can happen in nature. But fundamentally, the issue is that when you have channel data that are very ubiquitous, meaning, for example, the CSI information from commercial systems, and you can have terabytes of data from that very easily, but it's all uncalibrated and very difficult to interpret. And if you have precision measurement campaigns, then you very quickly get to a point where the number of data that you're getting as an input becomes rather limited. And if you make your neural networks too large, you very quickly get into the overfitting regime. So I think there is a lot of interesting research to be done, but for now, in my personal opinion, it's not quite at the same quality level as statistical models for practical applications.
I just wish people would say what you said more often, because every meeting I go to, it's like AI is going to solve world hunger when it comes to propagation. And so, and a lot of people are, I think, afraid to say the contrary to that, because maybe they're worried about their stock value going down or something. But anyway, I'm glad to hear you have some level of skepticism.
Well, I think if we have no more questions concerning the distributed massive MIMO, let me move on to the upper midband measurements. So I think the upper midband, again, in this forum here, not much need to discuss the motivation for it. So this is where a lot of the action in 3GPP is right now. The propagation in the close to 6 gigahertz bands are probably fairly well explored, especially because the 5 gigahertz band has already been measured quite extensively. But when we're going to the little bit higher frequency bands, right, around 12 gigahertz, where there is questions about interference with satellites, going to 18 gigahertz, then the available measurement results are much sparser. And so in order to get a little bit of a better feel of how do propagation characteristics actually change over frequency, we did 2 measurement campaigns on our campus that were double directional. We measured here over distances of up to about 440 meters. All of the measurements were either line of sight or obstructed line of sight, by which obstructed line of sight, I mean, there were trees in the way, there was vegetation in the way, but there were no buildings in the way. Now, one, I think, very important observation that I didn't put here on the slides is that the particular environment in which the measurements are happening is becoming really, really important at those frequencies. And so, for example, when we try to do non-line of sight measurements and move the receiver somewhere into a non-line of sight street, well, even if we just went maybe 20 meters around the corner, we pretty much saw no signal anymore, especially at the higher frequencies. And that is, of course, not exactly good if you want to have good coverage. On the other hand, our collaboration partners in Finland were doing measurements in a very densely built up environment, but where there was basically solid blocks of buildings and no shrubbery and other vegetation, and their communication around the corner worked pretty well. So this influence of vegetation and of these loose build-ups where there are no good reflection paths that get the radiation around the corner via reflections rather than diffraction, that can be a serious obstacle in obtaining decent coverage. So that being said, we, as I said, measured over large bandwidths. We analyzed our power delay profiles. So we were looking here both at the power delay profiles in the maximum directions of the horns, which we measured, as well as omnidirectional. And we saw that, well, with the horn antennas, the PDP has, or the maximum excess delay is not very large. The angular power spectra that we see overall are somewhat spread out, which in the street canyon with a bit of waveguiding is not very surprising. And maybe more important was to say that as we're looking at the path loss, well, that one really increases quite significantly with the frequency, and in particular, the path loss slope also increases with frequency. So it's not just that we are having the extra free space path loss, but rather that the impact of the attenuation process of the vegetation becomes stronger as we are going to higher frequencies. On the other hand, for delay spread and angular spread, we really didn't see too much change in as we were changing the frequencies from 6 to 14 gigahertz. We also already at an earlier time measured the frequency dependence of the delay spread. There we were actually going from 3 to 18 gigahertz, but that was an omnidirectional system. And we saw that if we use omnidirectional antennas, and very importantly, if we keep the dynamic range of the system independent of frequency, then we actually have a delay spread that's pretty much independent of frequency. And I'm stressing this because there is sort of this fork law that says that, oh, delay spread decreases with increasing frequency. And that needs to be interpreted very carefully. Because at increased frequencies, we usually have a higher noise floor, that means that the delay spread that we're observing tends to become smaller, but that's not really saying anything about the behavior of the multipath itself. And of course, if we have narrower beam width, then that also will reduce the delay spread. But if we really compare like for like, then delay spread is pretty much independent of frequency. So here is another measurement campaign in which we were very dedicatedly looking at the attenuation through frequency. And again, you see here that, yes, as we increase the frequency, the additional vegetation loss just goes up. So I think this is, again, a possibility to take a break and see if we have questions. Yes, Monisha?
Hi, Andy. Thanks for this. Couple of questions. When you took these measurements, you used horn antennas, right?
Yes.
And maybe you had the beam width on them, but what kind of beam widths were you using? And were you kind of pointing your transmit receiver beams at each other, so you were beam aligning both sides?
So the beam widths, I think, were around 15 degree. Let me see here. Okay, I somehow forgot to write that down, but yes, I think they were somewhere on the order of 15 degree. They actually changed slightly over the frequency range that we're looking at. But the measurements were actually directionally resolved. So we put the horn antennas on mechanical rotors and swept the whole thing. So that allowed us to synthesize an omnidirectional pattern like the red power delay profile that you see here, or to just do the selection of the best beam combination, which is the blue curve that we see here.
And the signal itself, was it continuous wave sounding signal, or did it have, like, for example, for 6G, people are talking about bandwidths up to 400 megahertz, right?
Yeah.
So you'll have a pretty good frequency diversity in that band. So what were the bandwidths of the signals that you were using to sound?
That was 8 gigahertz. So we
you were sounding with the full 8 gigahertz.
The full 8 gigahertz in 1 megahertz steps.
In 1 megahertz steps, okay.
So 300-meter delay resolution. We checked our environment. That was enough to avoid aliasing.
Okay. One of the things is, I think your results are very realistic, but when I look at some of the results that are being put out there by both Nokia and Ericsson, and they're using, I think, phased array, big panel antennas, and there are claims that 7 gigahertz will give you the same coverage as 3.5 gigahertz. And I look at those results a little bit skeptically, and I don't know if you have a feeling as to whether you can do that with just having bigger antenna arrays and some narrower beams, but then beam tracking becomes an issue. Do you have a sense of the trade-offs over there?
Well, I think there are some good possibilities there, and yeah, I mean, if we keep our antenna area constant and we actually can build the large enough arrays for the whole thing, then I think that good coverage can be achieved under certain circumstances. But I think my gut feeling is, or not just gut feeling, based on the measurements that we did and that our partners in Alto did, that this is extremely dependent on the environment. Yeah. And so if we are in a heavily vegetated area with this light build up the way that we are seeing here, then maybe for line of sight, we could get still more or less similar coverage. The moment that we're going around the corners here, I think we might be in severe trouble. But if we were saying that, no, let's rather go to downtown LA or downtown Finland or wherever, then I'm sure that there are a lot of environments in which the 7 gigahertz is performing very well, also in terms of coverage. So I think it will be a matter of picking and choosing where to use which frequency band in order to make the most out of things.
Thanks.
I think
Yeah,
Ed,
yeah, Andreas, appreciate you're looking at this range where you have multiple cells, because typically in a practical system, that's one of the more difficult areas to handle, where you have multiple strong cells and need to do the handoffs. And not only that, it's sort of also the time dependence. For example, if you have a moving UE, can you get I'll call it the measurements of the adjacent cells that you might want to hand off to, back up to the infrastructure and then down to the, within the command to, adjust, within a appreciable amount of time before you actually just get overwhelmed by a loss of signal or just not being able to do that handoff and the other cell gets too strong.
Yeah, I think those are important considerations. Now, that question about simultaneous link to the multiple cells, that I think is more or less aligned with the cell-free massive MIMO consideration. And because from a system point of view, of course, cell-free massive MIMO is very different. That you're saying you have joint. Everything is working together instead of competing and creating interference. But from a channel measurement and channel modeling point of view, it's the two things are extremely similar, right? Because you just need the joint characteristics from a UE to multiple base stations. So I think in that sense that these types of models and results should be helpful in that context. And I very much agree with you on the importance of considering all of these things.
Okay, thank you.
Yeah, then maybe let me first jump to the last two items, because each of them is a little bit shorter and we might overall otherwise run completely out of time if I next talk about terahertz. So as we are going to the higher frequencies, and that particularly means going above 60 gigahertz, one key question is, how can we actually do directionally resolved measurements? And fundamentally, we have three possibilities, or rather, until recently, we had two possibilities. One is to say we take horn antennas and we're mechanically rotating them with stepper motors. And that is the classical approach that's been used for millimeter wave channel measurements for a very long time, and has worked out great. But the problem is that they're inherently very slow. And in the terahertz section that I was discussing about, I am describing how basically doing a 360-degree sweep at both link ends for just one particular location pair of transmitter and receiver pretty much takes 5 to 8 hours. So we usually need it one night for doing one or two measurement points. And so it gets very, very tricky to do measurements where you're getting sufficient number of measurement locations. Now, of course, the better way of doing things is the use of phased arrays. And Molisch mentioned this already. Right? We actually have a millimeter wave sounder based on phased arrays from Professor Rebase's group at UCSD. And those are beautiful devices. You can measure within 100 microseconds or something like that, or maybe 1 to 10 milliseconds, the full double directional channel impulse response. And so that's all good. The problem is, what do you do in those frequency bands that are not yet commercially explored? Typically, people don't build phase arrays for frequency bands that are where there is no commercial application. And at these really high frequencies, let's say above 140 gigahertz, it also just becomes technologically almost impossible. So what we were asking ourselves is there a thing in the middle? And we were looking at these stepper rotors and we're saying that, well, what keeps them slow? It's the fact that we are slowly rotating and then we're stopping, waiting for the horn to stop wobbling, and then we're doing measurements. Well, what if we're just measuring continuously and rotating the horn continuously? Well, the problem with that is the cable is just going to roll itself around the around our tripod, and everything breaks. So our key idea here now was to say that let's actually separate the generation of the electromagnetic waves from the thing that moves or that points the beam into different directions. And so you see here, this is almost like a periscope. It's a plastic cylinder in which we have inserted a mirror inclined at 45 degrees. And now this tube is rotating. So the wave generation is happening down here. A horn antenna sends the waves upwards. And now this mirror redirects the wave in the horizontal plane into different directions of azimuth. So whenever that plastic tube rotates, then the beam direction rotates with it. And the nice thing is that now, because we have separated anything that needs cables and so on from this mechanical thing, we first of all can rotate continuously, and we can actually rotate enormously fast. And we can do 6,000 rotations per minute on this thing here. And this now means that we need approximately just 1 second for a full MIMO snapshot, as opposed to 4 or 5 hours. Right? So this leads to a speeding up by a factor of about 1,000. An additional nice thing here is that this is pretty much independent of frequency. I mean, the dimensions of your tube need to be a little bit adjusted if you're going from, let's say, 30 gigahertz to 140 gigahertz. But actually, we built a prototype for 60 gigahertz, and then we tried it out with 140, and it still worked. And so it's fairly broadband in this whole thing. So essentially what that means now is that if you have a SISO channel sounder, you can convert that to a MIMO sounder with nothing but adding on this mechanical component that you have here. So as I said, we built the prototype, and for 60 gigahertz, there are a lot of obviously details that go into the construction, from angular encoding, photoelectric sensors, and so on and so forth. But when we then did the measurements and we measured in an environment with known reflector locations, you see here the music evaluations, we were basically accurate in the identification within a couple of centimeters of the location of the reflectors. So we did comparison measurements also VNA plus precision rotor, and then measurement with this RAROMA device, and the results were in very, very strong agreement. The strength of the scatterers and so on that we saw, variations were somewhere on the order of 1 to 2 dB. And the original motivation for all of this stemmed from wanted to measure V2V channels at 60 gigahertz. And so after we spent several years on the construction of the sounder, then we actually went out and did some measurement campaigns. And we found that, first of all, obviously the line of sight component is the dominant one in this environment, not exactly surprising, and that we are getting reflections from various objects that are standing around near the street sidewalk and so on. So it's not only buildings, it's actually even relatively small objects like traffic signs at these high frequencies do play a major role. But I guess the main conclusion that I want to give here is that this REROMA is really a way in which you can find a compromise between the rotating horn with the stepper motor and the phased arrays in terms of the cost. Now, to also give the proper caveat, right? It's not REROMA is not as fast as a phased array, and it still needs about 1 second to do a full MIMO snapshot. A phased array manages the whole thing in something on the order of 5 milliseconds. So if you really want to extract Doppler, if you want to have a full MIMO snapshot within each coherence distance of the channel, then you just have to use a phased array. But if you're saying that, well, you're okay moving with in a dynamic environment, having 1 snapshot per stationarity distance, or if you're just saying, I want to be able to measure a lot of locations with stop and go, and saying that, okay, 1 measurement takes me about 10 seconds, and it takes me 3 seconds to move to the next location, and so on, right? You can probably measure more location pairs in 1 night than you can measure with this setup here in a month. Do we have any questions on this issue? I see none. Yeah, then one other thing I wanted to mention is about the modeling of line of sight. So I think most of us are familiar with the 3GPP channel model. That is basically just saying that, well, depending on the distance, my line of sight probability goes from 1 down to fairly small values. And depending on whether I'm in a urban macrocellular environment or in a rural environment, how fast this goes down is, well, that depends on the environment. The problem with this particular model is, first of all, it's based on a very small number of measurements. It was based on cities in Europe only. It doesn't distinguish between urban and metropolitan environments. And so if you have skyscrapers, things are different compared to you've got 5-story buildings. And last but not least, it says the model is constant overall cells. And that obviously you have variations in your line of sight probability from cell to cell. If you place things in this particular part of Los Angeles, in a different part of Los Angeles, well, the line of sight curves are not going to look exactly the same. So what we then did is we combined 2 data sets that are publicly available. One is OpenStreetMaps, which just gave us the footprints and heights of buildings pretty much throughout the US. And the other one is a database of the FCC, which gives us the location of every macro cellular base station in the US. So we got a total of 160,000 base stations with and analyzed the line of sight situation in a 1 kilometer radius around each of those base stations. We also created a classification of environments, which is a whole topic by itself, right? Neither 3GPP nor ITU really give a clear classification of when an environment is suburban or urban macro or metropolitan. So we derived our own classifications, and we then created 2 types of models. One is something that's fairly similar to the structure of the 3GPP model, meaning it is the same line of sight probability curve in every cell, as long as we're in the same environment. And so there we looked at, okay, if we look at rural macro environments, then we actually see that there's pretty strong agreement between what 3GPP did and what we are doing. When we're going to urban environments, we actually are seeing radical differences. And the blue curve here is the 3GPP model, and the black curve is what we get in a metropolitan environment, and the green curve is what we're getting in an urban environment. And so these are really 4 American cities based, as I said, on the whole country database. So I am in no position to say is that really the way that European cities differ from American cities, and the deployment in European cities is different. But in any case, the results are dramatically different here. The other aspect is also that we actually have variations from cell to cell, and we do have models for that as well. So we basically say that the decay constants in the cells are themselves random variables for which we can define probability density functions. And we actually just, I think a couple of weeks ago, got the acceptance notice for that paper. So all of the details are in there. But this is, I think, again, an important aspect to take into account, because if the line of sight probability is underestimated to this degree, in particular when we're looking at interference probability, and that plays now back into the loop of spectrum planning, then that is really a major factor or a major difference of what we see in that 3GPP model and what we should be expecting in a deployment in the US. So do we have questions on this issue? So I think, Nick, now a question to you is, I have a whole bunch of slides for terahertz, which I guess would take us at least another 15, 20 minutes, which might be too long for this forum. Should I just wrap it up at this point and maybe just say 2 minutes of what our key insights here were, or do you want me to spend a little bit more time on this?
Well, I will defer to the broader audience. I have to apologize, though. I'm signed up to participate in an MS thesis defense starting 1 minute ago. So if Monisha wants to continue, if she's able to stick on and help manage Q&A and MC, that would be great. Otherwise, maybe we can invite you back for another talk to go to these really high frequency frontiers.
Yeah, I think, given the interests of time and other people, I think getting Andy back would be a terrific idea to delve more into the terahertz, because I'm sure he can devote half an hour to 45 minutes on just that topic.
Yeah.
We don't want to lose plenty of people would probably have other commitments as well right now. We don't want to lose the audience.
Yeah, we typically schedule it from, for the 1 hour session. And I see at least one other person that said they have to drop off. So let me take the opportunity to thank you, Andy. Fascinating stuff. And hopefully we'll be able to share your slides in this video with the broader audience.
Yeah, I'll be happy to. And then, thank you very much, Nick, again. And so maybe I'll just present a summary and some final slides, and then I guess if there are more Q&As, I'll be happy to stay on. But I know we are all busy, and probably a lot of people will be have commitments already for.
Yeah, a number of folks are dropping off, but I take your point there at the bottom. I couldn't agree more.
Yep. Yeah, I think everybody will appreciate that we need more work on propagation. So.
Yeah.
Well, thanks again, Andy. Let's thank everybody. Thank Andy. Stay tuned for the next Radio Shop chat. perhaps by Andy Molisch. Bye now.
So, yeah, then maybe just to do the summary and conclusions. So I know I said it in the beginning, but I think it's always good to summarize the key points in the end. So when we're dealing with distributed MIMO systems, first of all, from a measurement point of view, we have to come up with some new ideas, in particular dealing with using virtual APs. And so we presented the two methods with a drone or with a rolling cherry picker to achieve that. And from a modeling point of view, that the Euclidean distance only path loss law simply does not work for these urban applications, but rather that we have a path loss that depends on or changes street by street, depends on the street order, and also point I didn't go into too much detail, that shadowing is non-stationary now. So it's not just a function of the distance difference between the considered locations. For the upper mid-band, we should inquire more about what are the full band characteristics, not just sort of what's happening in the very lowest part, because sooner or later we're going to branch out to higher frequencies as well, even if things are starting at 7 gigahertz. And obstruction by vegetation is a really critical thing in that band. When it comes to measurement principles, switch beam is a great solution when phased arrays are available, but if that is not the case, then this array-ROMA is actually a possibility for doing sounding in a much faster way than what can be achieved with the traditional stepper motor. And if you're interested in more details on this, also I'm happy to discuss this. Right, as I said, we have a prototype, we have a patent on this. We would be happy to collaborate with anybody who wants to build something along those lines for their lab as well. And then finally, when it comes to the line of sight probability, we found that even the sort of average line of sight models that are around in 3GPP are not a proper fit for the real world deployments in the US, in particular in urban environments. And that secondly, it's important to take into account that the line of sight probability itself is experiencing statistical variations from one cell to the other. And while you're not going to read now these references, I'll include them in the slides that are going to be distributed. So if you need more information, we have the various journal and conference papers for the different topics. And with that, I would like to conclude with some thanks, right? As you can imagine, this is not my work. This is the work of a huge team of people. So I especially want to thank my postdocs and students here at the USC, and also all of our collaborators, Alan Wilner and his team, Charlie Zhang and his team at Samsung Research America, Katsu Haneda at Alto, ComCenter, and then the organizations that funded a lot of our work, SRC, NSF, and IST, and our industrial affiliates. And if you are interested in the papers that I was just listing here, we have actually the PDFs of all of them available on our website here as well. With that, thank you very much for your attention. And yeah, if there are more questions, happy to answer them now.
All right, I'll step in real quick, Andy. Emily Case, nice to see you on Zoom here. But hearing no questions, I think we can go ahead and call it. And thank you so much for your time today.
Yeah, thank you very much. It was great to be here. Appreciate it.